Hey, welcome to Unit 4 over Analytical Trigonometry. In this video, we're going to talk about the law of sines. So we're going to kind of step away from verifying expressions and equations and solving. We're going to go back to the wonderful, beautiful, amazing world of triangles. Now, let's remember that we learned a lot about trigonometry when it comes to right triangles. So what do we do if we have non-right triangles? Well, all of the trig functions that we've learned, sine, cosine, tangent, they don't work unless you're in a right triangle. The whole idea of opposite, hypotenuse, and adjacent is founded on an idea that it's true for right triangles. So what do you do if you have a triangle that's not a right triangle? Well, actually in the past, we have looked at problems like this. So I want to kind of stay generic here. So imagine we have a triangle, and I'm going to call the angles capital A, capital B, capital C, and then I'm going to call the sides lowercase. So across from the A is going to be lowercase a, across from the B is going to be lowercase b, and across from the big C is going to be lowercase c. So remember, we saw problems like this before where I give you, let's say that I give you an angle, I give you a side, and I give you another angle, and I ask for maybe like this missing side, we'll call it A. Or B. The point is, I give you a couple things, but I don't give everything, and it's not a right triangle. So like, okay, well, what do we do? Well, remember what we did was we said, well, if you don't have a right triangle, you can always make one. So, for example, we could take this vertice right here, B, and from B, we could come straight down, forming two right triangles. So we got a right triangle number 1 and right triangle number 2. And then again, I believe that we did a lot with tangent because we had to understand that this side, this imaginary side, I guess you could say, that I just created, which is the height of the triangle, we'll call that x. We had to use that value because that x was shared between the two triangles. The triangle 1 and triangle 2, the one thing they have in common is x. So we used that, and we had to find ways to solve, again, using trigonometry from this. But from this setup, we actually get something that's really cool. And that's what I really want to talk about in this video. So looking at this setup, I just want to kind of take a look at a couple things. Let's look at triangle number 1. And if I say, hey, let's talk about sine of angle A. So sine of angle A is looking in triangle 1 here. And according to angle A, sine is the opposite, which would be the shared side x, divided by its hypotenuse. And again, according to triangle 1, the hypotenuse is little c. And then let's look at angle C for a second. So if we look at angle C, so we have sine of angle C. Again, according to triangle number 2, the side opposite of angle C is that connected side x. And then again, the hypotenuse in triangle number 2 is little a. So notice that the only thing that is connected, the only thing that is the same between these two triangles, because there's no guarantee that angle A and angle C are going to be the same. There's certainly no guarantee that side C and side A are going to be the same. But I do know without a shadow of a doubt that X is the same. So what I can actually do is solve for X. So I'm going to multiply by C, so I get C times sine of angle A equals X, and I can multiply by X over here as well. Or, excuse me, I could solve for X by multiplying by A. A times sine of C equals X. And what I do know is that X equals X, right? The X from the left triangle, number 1, is certainly the exact same as the X from the right triangle. So I know that C times sine of A equals A times sine of C. So again, I'm just trying to make some logical connections between the angles and the sides of this triangle. Now, what I want to do next is kind of unique. But again, what I want you to understand is that even though angle A, angle C, side A, sine C are all potentially different, I do know that this statement right here is a true statement. C times sine of A equals A times sine of C. Awesome. Now, one thing I could do is I could divide everything by AC. As long as you divide everything by the same number, you might be changing how it looks, but you're not actually changing it. So if I divide the left side by A times C, the C's are going to reduce out, and I get sine of big A divided by little a equals on the right-hand side here. If I divide by AC, the A's cancel out, and I get sine of C divided by little c. So what's interesting is this, is that even though this is a non-right triangle, I could make it a right triangle. In fact, I can make two right triangles by drawing the height in there. And this allows me to see some definite connections between triangle 1 and triangle 2. And what I find out is that these ratios, sine of angle A divided by little a, the side across from it, that ratio is the same as sine of C divided by little c. And these ratios are what can help me find values. Even though this is a non-right triangle, I could use this ratio to help me find values. And this ratio that exists between the sines is actually called the law of sines. And I could even do the same thing for angle B. If I were to, redraw the triangle from a different perspective, I could see the same thing from angle B. So here is the setup that we're going to use, right? This is the setup where the angles are the capital letters, and again, these side lengths are across. So little a is across from big A, little b is across from big B, and little c is across from big C. And this leads us to the law of sines. So the law of sines is telling us that there is a unique ratio, not ration, what the heck, I can't type. There's a unique ratio between the sine of an angle and the side across from it. In any triangle, it doesn't even have to be a right triangle, in any triangle, that ratio is the same between all three angles and all three sides across from them. And you can actually write the law of sines either way. You could have the sides be on top and the sines be on the bottom, or you could have the sines be on top and the lengths on the bottom. I usually go with this format right here. And again, this is awesome. This is a great ratio, and this is a magic, super cool ratio that I just proved in the example that I was just doing with you a moment ago. But the theory, the law simply says that there is a ratio that exists. I mean, ratio is a division, right? A over B is a ratio. So again, the ratio is that if you take sine of an angle and divide it by the side across from it, you're going to get a ratio. This is going to be a number. And that ratio is the same for the other pairs of angles and sides. Again, this is really cool. So again, what this is saying is that if I take sine of angle A and I divide it by little a, the side across from it, that ratio, whatever it is, let's just call it R, that ratio, that number, is going to be the exact same if I do sine of angle B divided by little b. Even though angle B is going to be different than angle A, even though little b is going to be different than little a, the ratio dividing them is going to be that same ratio in this triangle. And it also is true for angle C. So once again, sine of angle C divided by the side across from it, little c, even though angle C is different than A and B, even though side C is different than little a and little b, the ratio of these three values are all going to be the same in any given triangle. And that is the law of sines. It's so powerful. And this law allows me to solve for angles and sides within a non-right triangle. Now, there is only one drawback. You're only allowed to use the law of sines if you know that ratio. So I need to know both an angle and the length of the side across from it. You could use law of sines anytime you know an angle and the side across from it. Again, I need to know the ratio. I need to know what that magic ratio R is. The only way I could find that ratio is if I know either both B's, both A's, or both C's. So once I find that magic ratio, whether I use the C's, the A's, or the B's, that magic ratio is going to be the same for the other values in that triangle. So there are three scenarios where we could use the law of sines. And going back to geometry, this might sound familiar. We could do in the angle, side scenario. So if I know an angle, and the next side, so two angles and the next side, I could use it. Now, why can I use it? Because just look at my picture. I'm circling what I know. So if I know an angle and the side across from it, I could use the law of sine. So an AAS scenario, I can use it. Another scenario is the angle-side angle. So if I know an angle, a side, and the next angle, so if I know two angles and the side in between them, I could also use the law of sines. Now, some people might look at this and say, oh, no, you cannot, Mr. Princhak. You don't know both an angle and the side across from it. Yes, you do, guys. Because anytime you know two angles, you automatically could calculate the third because you know all the angles of a triangle add up to 180. So even though I don't initially know this angle, if you know two angles, yes, you do. And then I do know an angle and the side across from it, so the law of sines can be used. It could also be used in the ASS scenario, angle, side, side, because again, based on this scenario, I do know an angle and the side across from it. So anytime you are posed with a triangle where you know an angle and the side across from it, you could use the law of sines to solve for anything else that you want. Now, at this point, you might be like, all right, great, but how do I do the work? And that's what we're going to do right now. So let's look at an example here. So first off, I'm giving you big C, big B, and little b. So right away, I know both b's. That's the sign I could use the law of sines. Now, one thing I'd like to do is to draw a picture. Like I've told you guys 1,000 times, a picture in trigonometry is worth 100,000 bazillion words. So I don't even care if your picture is accurate. That actually doesn't matter to me at all. I just care that you could draw it. So once again, let's label A, B, C. It does not have to be accurate. And let's label little a, little b, little c, and then again, we can fill in the blanks. I know big B is 28.7. I know big C, even though it certainly doesn't look like it, it doesn't matter. I'm just trying to make a picture for picture's sake. There's big C. And then I also know little b is 27.4. Now, what do I have to do in this problem? Well, we have to solve the triangle. Now remember, solving the triangle means finding all angles and all sides. All right, so let's get rid of the obvious. If you know two angles, you could always find the other angle by simply adding what you have together and subtracting from 180. So I'm going to go ahead and do that right now on my calculator. If I know that one angle is 102.3, add the other angle, 28.7. So far I have 131 degrees. So now I'm going to take 180 degrees that I know are in a unit circle. What am I talking about? I'm thinking too much trick here. That are in any triangle. All triangles have 180 degrees. I'm going to subtract the 131 and I get 49 degrees. So that missing angle A is 49 degrees. All right, so that actually was not using the law of sines. I was just using geometry. Now I need to use the law of sines to find the remaining two sides, little a and little c. All right, and now again, I need that magic ratio. I know that sine of 28.7 degrees divided by the side across from it, little b, 27.4, that ratio right there is the same magic ratio as it is for angle A and angle C. So the first thing I want to do is I want to discover what that magic ratio is. So please make sure you're in degree mode because this is definitely a degree problem. So go into degree mode here, and I'm going to type in sine of 28.7, and I'm going to try to type it in, okay. I'm having some problems typing on my calculator right now. Sine of 28.7, please make sure you close that parenthesis, and then divide by the 27.4. That magic ratio is 0.0175, 0.0175. And what I'm telling you is that if I take sine of angle C, 102.3, and divide it by little c, which I don't know, but I do know that I'm going to get that same exact magic ratio, guaranteed. So now I can easily solve for C. And I'm going to do the same thing for A, because I know that sine of 49 degrees, angle A, divided by little a, the side across from it, is also equal to that super special magic ratio. Again, whether you choose angle A, B, or C, the sine divided by the side across from it is going to be the same. So this is going to enable me to easily solve for C and A. All right, so what I'm going to do is I'm going to multiply the C over to here, and then C is going to equal, because now I have to solve for little c after I multiply it up. When you multiply, it cancels it out down here. So I'm going to take sine of 102.3 degrees. I'm going to divide by that ratio, 0.0175, to solve for little c. Now, watch how I'm going to do this on my calculator, because I want to be super accurate on my calculator. So just kind of pay attention how I type this in. I'm going to do sine of 102.3. I'm going to close that parenthesis. And instead of dividing by 0.0175, which is rounded, I'm actually going to go and grab all of those decimals to be super exact. So there I go, 55.747. 55.747 is the length of side C. And I'm going to repeat myself and do the same thing for A. I'm going to multiply the A over to here. And then to solve for A, I'm going to take sine of 49 degrees, and I'm going to divide it by the 0.0175. But of course, when I go to my calculator, I'm going to be very careful, not cosine, sine of 49 degrees, close the parenthesis. And again, instead of dividing by a rounded number, I'm going to go back up here. I'm going to grab all of those decimals, and I get 43.061. So little a is 43.061. So again, even though this was a non-right triangle, I was still able to use a little bit of trigonometry through the law of sines to find the angles and the sides that I needed. Pretty cool. All right, let's do another one. All right, this time at first glance, it does not look like I know both A's, both B's, or both C's. And remember, you need to know both an angle and the side across from it if you're going to use the law of sines. But after you make your picture, you will easily discover that I do know enough information. So once again, let's quickly label this A, B, C. It does not have to be very well drawn. Obviously, this looks like crap, but you get the point. I'm given angle A is 43 degrees. I'm given angle B is 98 degrees. And I'm given little c is 22. Now, the problem is that to use the law of sines, I need to know both B's, both A's, or both C's. But I do know angle C because I can use geometry, not trigonometry, to quickly find angle C. All I got to do is take 98 plus 43, add the two angles we have so far, and then do 180 minus that, and now I get that angle C is 39 degrees. All right, now I could go ahead and find that super special magic ratio. Sine of 39 degrees divided by the side across from it, 22, is my magic ratio. So sine of 39 degrees, close that parenthesis, divided by 22, nope, not 222, 22. There it is, 0.0286. And in this triangle, that magic ratio is the same for all angles and all sides. So sine of 98 degrees, that's angle B, divided by little b is also 0.0286. Sine of 43 degrees, which is angle A, divided by little a, is also 0.0286. Again, this is the magic of the law of sines. So now I just got to solve. I'm going to multiply the b over to here, and then to solve for b, I'm going to take sine of 98 degrees, and I'm going to divide by the 0.0286. And before I go to my calculator, I'm going to do the same thing for A here. Multiply the A over to here. And then to solve for A, I'm going to take sine of 43 degrees. I'm going to divide it by the 0.0286 as well. But once again, be careful, because when I actually go to my calculator, I'm going to type in sine of 98 degrees, close that parenthesis, divided by, and I'm going to go and grab all those decimals so I'm super accurate. So therefore, little b is 34.618. And I'm going to do the same thing for A, sine of 43 degrees divided by, again, I'm going to go and grab all those decimals, is 23.842. So little b is 34.618. There's little b. And little a, I forget what it was, I got to go back, 23.842. 23.842. How cool and simple and easy is all of that? So awesome. It really is an easy law, and it's awesome. So go back to those triangle problems that we had in the beginning of this unit. and in Unit 3 that were like really tough and sucked, and we had to do a ton of algebra. Now we really don't have to do that much work at all. The law of sines is going to help us with those problems. Sorry I didn't tell you about it until now. All right, but there is one thing that's an issue to us. The ASS scenario, and again, it's an ambiguous case. This isn't a scenario where we got to do a little extra thinking. And in geometry, you learn that the ASS scenario is a bad scenario, but I don't want to connect this too much with geometry. But obviously, ASS spells something that isn't great, and that's the reminder that this is going to be a tougher problem. So the issue is this. In the ASS scenario, there are actually 3 situations that can occur. You could have no triangle. No triangle. You could have 1 triangle or 2 triangles. And for some kids, this is a little bit confusing, so let me explain. If I have a side and an angle, and there I am, right? I have an angle, I have a side, and another side. Now, here's the scenario, right? If I know these 3 things, if I know this angle right here, this side right here, and this side right here, the first scenario is that this second side is too short that it can't even connect to make a triangle. Like it's just kind of dangling there. And it's just dangling and it's too short, I can't make a triangle. So that's an example where no such triangle exists. It's the ASS scenario, and that second side is just too short, it cannot make it. The second scenario is that second side is the perfect length to create one and only one triangle. Swing it too far this way, can't make a triangle. Swing it too far this way, can't make a triangle. But swing it just perfectly right to here, you will get one triangle. But there's another scenario where this second side is a really cool length, where you could swing it in to create a triangle, or you could swing it out to create a second triangle. So we have this triangle right here, a little smaller triangle, and then we have this bigger triangle right here that is also possible. So the issue is that second side can either be too short to even make one triangle, it can't make any triangles. It could be the perfect length that makes only one triangle, or it could potentially make 2 triangles. So the key is to find the angle between the 2 sides first. So the key is to find this angle right here between the 2 sides. This angle could have another option. Now, this is why it's called the ambiguous case. Ambiguous means it's kind of cloudy. Like, I don't know, do I have one answer? Do I have 2 answers? Or maybe I have no answers. And this is something that you only have to worry about in the ASS scenario. So the answer is, how do you recognize this? Well, first off, the no solution case is really easy because when you go to your calculator, it's going to tell you no solution. So you pretty much know right away it's not possible. The second scenario is that if there is a second option, then you have to take the first angle you get and subtract 180 or do 180 minus that angle. And then this will tell you if there is a second option available. Now listen, I can sit here all day and talk about the ambiguous case, but until we look at some examples, you're never going to understand it. So let's look at an example here. All right, so I have 2 sides, little a, little b, and the angle A. So let me just draw a quick picture. That way you can recognize that this is the ASS scenario. So there's A, big B, big C, little c. All right, I'm giving you that little a is 85 degrees. I'm sorry, capital A is 85 degrees. And I don't know anything else. Little a is 15 and little b is 25. So first and foremost, why am I allowed to use the law of sines on this problem? Because I know both a's. So my magic ratio is that sine of 85 degrees divided by 15 is going to be my magic ratio that I'll find in 1 second. But this is an ambiguous case because it's the angle side scenario. So the trick is to find angle C first. Find the angle in between them. So let me talk about how we're going to do that. All right, so let's see here. First, I have to understand that I can use the law of sines because I do know angle and the side across from it. So let me go ahead and get that magic ratio because that's the first thing that's pretty easy to do. All right, so sine of 85 degrees divided by 15, don't forget to close that parenthesis, by the way, is 0.0664. 0.0664. Okay, so now again, let's see what I could do here. Well, I can't find angle C right away. Because again, I don't know little c, I don't know big C. Do not you dare try to use Pythagorean theorem. That only works on right triangles. So I guess I'm going to have, the only thing I could actually find right now is angle B. Because I know this, right? This is the law of sines. I know that sine of big B divided by 25, little b, is going to be that same magic ratio. Now, this is true for C as well. I know that sine of big C, which I don't know, divided by little c, which I don't know, equals 0.0664. And that's why I can't do anything with C yet, because I need to work on B first. All right, so let's solve for B. I'm going to multiply both sides by 25. So multiply both sides by 25 cancels this out. And I get sine of big B equals 0.0664 times 25. Now, how do I find B? How do I find an angle? Oh, come on. Pull the old switcheroo. B equals the inverse sine of 0.0664 times 25. So now I'm going to go to my calculator to get angle B, and be very careful how you type this in. Watch what I'm going to do here. Inverse sine. And I'm going to go ahead and do 25 times, and instead of rounding to 0.064, I'm going to go and grab all those decimals, and error? Can't do it? Well, there you go. No solution. The calculator is telling you that no such angle B exists that allows for this to happen. And that's why we're going to just stop here and write no solutions. So what's happening here is that even though I drew the picture, remember I was just drawing it based on what I knew, but what happens is that this 15 is too short. So in reality, it's going to end like right here, and it's not even going to be able to connect with that bottom side to make a triangle. All right, so let's look at another problem that does work out here. So once again, let's quickly draw the triangle. It does not have to be very accurate. A, B, little b, C, little c. I know angle A is 42 degrees. I know little a is 22. I know little b is 12. And once again, I don't know anything else. So I am going to use the law of sines here because I do know sine of A, 42 degrees, divided by little a, 22, is my magic ratio, which I'll find in a second. But again, I do need to recognize that this is going to be a problem that's going to make me think because I have an angle, side, sides. This is that ASS scenario that always causes headaches. And again, it's an ambiguous case. So in the previous problem, I figured it out. There was no solutions. What's going to happen here? Let's find out. So once again, I'm going to go ahead and find that magic ratio. So sine of 42 degrees divided by 22 is 0.0304. 0.0304. Now, sine of big B divided by little b, 12, is going to be that same magic ratio. And the same thing could be said for angle C as well. But again, the problem is I don't know either one of these. I don't know big C, I don't know little c, so that's actually not going to do me any good right now. So, okay, how do I solve this? Let's go ahead and multiply by 12 to cancel this out. And I get sine of big B equals 12 times 0.0304. And to solve for an angle, we're going to simply pull the old switcheroo. All right, now when I go to my calculator, once again, be very careful. Watch how I type this in. I'm going to go ahead and do an inverse sine of 12 times, but I'm actually going to go up here and grab all those decimals. That way I don't do any rounding. And I get, okay, now I did get an answer. So 21.41 degrees. So big B is 21.41 degrees. Pretty easy. I mean, look at that. Again, previous problems couldn't do it. So I just knew right away there's no solution. Here I know there's a solution. All right, so now I got big B. Now, here's the deal. And this is what's tricky. Again, all we can do is practice this. There is a potential for a second solution. So I'm going to come over here. There is a potential for a second angle B. And to find that, we're going to do 180 minus 21.41. That's the trick. So if you only have to worry about this in the ASS scenario. And once you do get that angle B, you're going to go ahead and find a potential second answer for angle B. And to get that second answer, you just do 180 minus 21.41. Sorry, 21, and typing on this screen here is really hard. I'm so sorry. 21, boy, oh boy, 21.41. There we go. Finally, I'm capable of doing it. 158.59 degrees. 158.59 degrees. Okay, now, how do I find the remaining angle? Big C. Well, come on, guys. Come on. I already know angle A is 42. I just found angle B to be 21.4. So to find big C, I'm going to go ahead and take 180 total degrees in a triangle. I'm going to subtract 42. That was angle A. I'm going to subtract 21.41. That was angle B. And now I get C is 116.59 degrees. So there is my options for angle B and angle C. Now I'm going to come over here. My second option for angle B was 158.59. What's my second option for angle C? Well, once again, we're going to go to the calculator because I already know A is 42 degrees. So I'm going to take 180. I'm going to subtract 42 degrees. I'm going to subtract the second potential value for angle B, 158.59, and I get negative? Wait a minute, an angle can't be negative. What that is alerting me to is that there is no second option. I had to try and see if there was one, but it just didn't work out. What are you going to do? Not the end of the world. So the only option for angle B is 21.41, and the only option for angle C is 116.59. So this is a perfect triangle that there's only one way to draw it, and that's with these three angles. So the only thing left to find is little c. So again, we can do sine of 116.59 degrees divided by little c equals, guess what? That same ratio. That ratio is never going to change. And I'm not going to waste your time right now. You could easily solve that for C. But again, the big thing in this problem was recognizing that second option for B, I thought it was going to work. I did get a value for B, but it was too big that all of the 180 degrees was used, and I didn't even have a possible for that second angle. All right, so let's look at the third scenario here. So this one is going to create two solutions, and I really want you guys to be able to see this. All right, well, that's a bad triangle. All right, capital A, capital B, capital C, little c. I'm given A is 20.5 degrees, little a is 12, little b is 31. So once again, this is the angle side scenario. Definitely one that's going to make me think. But going into the problem, even if you don't understand the ambiguous case, which I hope you do after this, but you're going to say, hey, listen, I know A, 20.5 degrees, and I know little a, 12, so I could go ahead and use the law of sines to get that extra special ratio. So here we go, sine of 20.5. I'm so sorry, I have such issues with this typing. It's this notepad I'm trying to use here. I'm so sorry. All right, don't forget to close that parenthesis, divided by 12. And the magic ratio is 0.0292, 0.0292. Okay, so once again, I can't do anything with C right now because I don't know big C, I don't know little c. So I'm going to go ahead and find big B. Sine of big B divided by little b, 31, equals, guess what? That same magic ratio. So now I'm going to go ahead and multiply by 31 to solve. And I get sine of big B equals 0.0292 times 31. To solve for B, I'm going to pull the old switcheroo with an inverse. So that's going to be 31 times 0.0292. But check it out. When I go to my calculator, I'm going to be very careful. Inverse sine, I'm going to do 31 times. And then again, to be honest, you could use 0.0292. You're not going to be that far off, but I'd rather be more accurate by using all those decimals. And I get B equals 64. Sorry, I took that away so fast. 64.78 degrees. So that is the first option for B, and that's definitely going to work. To find angle C, all I'm going to do is say, well, all right, well, I have 180 degrees in a triangle. I'm going to subtract the 20.5 I know are right from angle A. I'm going to subtract the 64.78 from angle B, and I get 94.72 for angle C. So this is my first option of my triangle where I have angle A, angle B, angle C. Awesome, check, check. But remember, and I can't stress this enough, the only time you have to worry about this is in the ASS scenario. So in this scenario, only do I have to say, well, wait a minute, there could be a second option for B. To find that second option, you just take 180 minus B, which is 64.78 degrees. And this tells me that the second option, 180 minus 64.78, is 115.22 degrees. Okay, so if B is 115.22 degrees, what would the second option for angle C be? Well, once again, I'm going to go to my calculator. I'm going to take 180 degrees. I'm going to subtract the 20.5 from angle A. I'm going to subtract the 115.22 from angle B. And this time, I do get a possibility for the second option. So it'd be 44.28 degrees. 44.28 degrees. So there's actually two possible triangles, and maybe drawing this could actually help. So here we go. Here's the deal, is that this third side could be swung in to make this triangle, or it could be swung out here to be this triangle. So notice that angle A right here, 20.5 degrees, is not going to change, but angle C could be 94.72 or 44.28. It all depends how you swing that third side. And that's what's happening here. In the very first example we saw, the side was too short. It couldn't even touch the third side, hence no triangle. In the second example we looked at a moment ago, that second side, or excuse me, that third side, it was just perfect enough to create one triangle. But in this example, there are two distinct possible triangles. A, B, C, that's one triangle, or the second option is again A, B, C. So there's two different triangles that come out. So you know what? The law of sines is so easy. I don't want this to be a downer at the end of this video. The law of sines is unbelievably powerful and unbelievably easy, but there's the only scenario that you have to sweat a little bit is the ASS scenario. So if anything, the abbreviation ASS spells something that should alert you that this is going to be a really hard problem. It's not hard. You just have to consider the possibility of a second triangle, or maybe there's no triangle. So, oh boy, I know this is a long video, but please pay attention. I had to take some time to really explain to this ambiguous case. If you don't have the ambiguous case, if you have an AAS scenario or an ASA scenario, you don't have to worry about this ambiguous case at all. You only have to worry about it in the ASS scenario. All right, guys, that's it for this video. Definitely going to need some practice with this to make sure we're good at it. But just know this, at the end of the day, it's actually really, really easy. Hope you believe me.